Well, greetings everybody. So I'd like to show you this problem from our assignment, and it is, despite how complicated it might seem when you read it, maybe the notation seems complicated or the description seems complicated. It's not that hard to work. Uh, but I put this problem on the assignment because it opens the door to some other issues that we need to talk about at some point. Okay. So although the problem is simple, and I guess I could just get right to the point and tell you how to work it, it's really not that bad. The calculations are not difficult or anything like that. This video will still be longer than I might like it to be, but that's the nature of calculus. Not every video or explanation can be short. Okay. Uh, Now the nature. So at this point, I'm not going to start by solving this problem. This opens the door to some other things that I need to talk about. If you were to skip forward in the video, you could get to the point where I just work this if that's what you're interested in. Okay. Now, what this opens the door to is this. So here's a problem that I've already made a video for, and it asks us to find the absolute extrema for this function on that interval. And part of that process was to locate these things called critical points. Okay. And critical points are points on the curve such that the derivative is 0 or the derivative is undefined. And it's this aspect that I need to talk about in some detail. What does it mean for the derivative to be undefined? Now, once I go over the possibilities for that, then I'll come work this problem. And I want that to lead into working this problem. All right. So I have given this some thought, and I hope it helps you as far as the big picture goes. So critical numbers, you can also call it a critical point, some point where the derivative is 0 or undefined. And like I said, all I want to concern myself with now is what does that mean if the derivative is undefined, because that's not something that I've talked about in the class yet. So there are three possibilities, I would say. Okay. The first possibility for what could be happening if the derivative was undefined at a certain spot or at a certain point, and that would be one way you could have a critical number on a curve, is that it might just be that the curve is not continuous at that point. Okay. In order for the derivative to have an answer, the curve would have to at least be continuous at that point. So here's an example, like this curve right here. This is a piecewise function, and it's not continuous at 2 because there's a jump discontinuity, and it's not continuous at 4 just because there's not a point at 4. Okay, this definition just doesn't give us any information about what the function is if x is 4. So that point's open, and then here there's a jump. Now, it would be true as a result that the derivative would be undefined at 2 and at 4, just because the curve's not continuous there. All right. So we might say that f prime 2 and f prime 4 are undefined. All right, so that's the first possibility. If the curve is not continuous, the derivative can't have an answer there. The derivative is undefined at any points where the curve is not continuous. First possibility. The second possibility is that the curve could have a vertical tangent or a cusp at that point. Okay, and I'll define what each of these are. So I've drawn some curves here. This is what a cusp looks like, and this is what a vertical tangent looks like. Okay, at this point and that point, the curves are essentially vertical, but in different ways. So that's the simple way to say it. I could just say, look, this is a cusp, and look, this is a vertical tangent, and I could say no more about it. But doing some math does involve studying some technical things. So it would be wrong if I didn't tell you what these meant as far as math goes. So if there's a cusp at some point C on a curve, it just means that the derivatives at that point go to either infinity or negative infinity from the left to right. You'll get opposite infinities. Okay. And I mean, that kind of bothers me how technical that is, but that's the kind of thing you need to see. Maybe you could think of it like this. if I zoom into this point, I'll see that left of where that cusp is, the curve gets steeper more and more and more in a negative direction, but to the right, the curve gets steeper more and more in a positive direction. It'd be nice to visualize that, I think. All right, so I'm going to do this. Here's a curve that happens to have a cusp at 0. All right, and what I'm predicting is if I zoom in more and more and more to 0, it'll get steeper in a negative direction just left of 0 and steeper in a positive direction just right of 0. That's what I mean by if you take the derivative and you have the limit on either side of the cusp, you'll get opposite infinities for the answer or the slope. One thing the derivative tells us is the slope of the curve. So let's zoom in more and more and more until we see like an infinitely steep negative line, or what seems to be that, and on one side, and an infinitely steep positive line on the other side. So I'm going to zoom in. We should see it get steeper and steeper. So here's 0. It does look like it's getting steeper negatively on this side and positively on that side. But let's keep going. Okay, now I see it's exaggerated even more. See, this is getting pretty steep in a negative direction. This has a negative slope. It's getting steeper, positive there. Now we can keep going as much as you want. And like here, like I am near vertical. That is almost vertical with a slight negative slope. And then on the other side, it's almost vertical with a slight positive slope. Or I guess I should say extreme positive and negative slopes. But there you go. That's what I'm trying to tell you right here. That's what it means if the curve has a cusp. As far as a vertical tangent goes, that just means that, if I was to zoom in on this little piece of that curve, it would look like a vertical line, okay? It just means that if you take C, the point where there's a vertical tangent, and you have the derivative and you take the limit for the derivative left or right of C, you're going to get infinity on both sides, okay? Now again, if you like visualizing, we can look at that. Here's a curve that has a vertical tangent at 0. So if I were to look closer and closer, this picture should smooth out into what looks like a vertical line at 0. But let's see if that happens. If it's got a vertical tangent there, that's what should happen. Okay, and I'm starting to see that. See, now we're looking pretty close to the point where x is 0, which is where this curve happens to have a vertical tangent. And I'm seeing this line in red. I don't see the curve anymore. I just see this, what looks like a line in red that looks nearly vertical. Okay, so those are some other cases where the derivative would be undefined. There's no derivative right there at the cusp. There's no derivative right there at the point where there's a vertical tangent. Now, the curves I just showed you the graphs for were f of x is x to the 2/3 power, which has a cusp at 0, and f of x is x to the 1/3 power, which has a vertical tangent at 0. There are their derivatives, okay? Is this derivative undefined at 0? Yeah, if you put 0 in there, you don't get an answer. It happens to be undefined, though, because there's a cusp. And you see this one, here's your derivative of x to the 1/3 power. Is it undefined at 0? Sure. If you put 0 into that, you don't get an answer. You'll be dividing by 0. It's undefined. Why is it undefined? Because this one happens to have a vertical tangent, all right? So it'd be hard to tell just from the fact that both of these derivatives are undefined, that one has a cusp and the other has a vertical tangent. But if we explored the graphs as I showed you just a second ago, or looked at these definitions, then we could tell the difference, all right? That's one way to think about it. All right, so there's the second possibility. The derivative might be undefined because there's a cusp or a vertical tangent. And the last and third possibility that concerns us with this problem here is that there is a corner point at C. Okay, so here's an example of a curve with a corner point. If we have a corner point, then the slope on one side of the corner is just different than the slope on the other side. Okay, and what do I mean by that? Normally, if we think about the derivative and we look at the slope of a curve, all I mean is that the curve itself doesn't have a slope. Well, you see this curve? There is no way for me to tell you what the slope of this curve is Now, I can tell you the slope of the curve at any point if I look close enough, right? It smooths out into a straight line, all right? So like now, if like at a close enough perspective, I can tell you the slope of a curve because at a close enough perspective, it will begin to look straight. That's what all the derivative is really, all right? So if I were to zoom in on a corner point, I just see more of the corner. It doesn't smooth out into anything that has a slope. It doesn't smooth out into a line. So that's what a corner point is. So here's a graph that has a corner point. So unlike this one, where as I zoomed in, what looked like a curve began to look like a straight line, that's not going to happen here. As I zoom in on that corner, I'm just going to see more of the corner. It will never smooth out into a line. It will never smooth out into anything that I can measure the slope of. And for that reason, there's no way that I can tell you what the derivative is right there where that corner is. I'm looking closer and closer, and all it looks like is the corner, right? What did this other one do? It smoothed out. The curve vanished, and I began to see a line, all right? So that's a kind of a simple way to say it. But I guess it'll be wrong if I didn't at least mention the more technical aspect. That means that the left-hand derivative at the corner is not the same as the right-hand derivative. Here's our original definition of the derivative. And do you see that limit as h goes to 0 right there? Oh, that's supposed to be an h. I'm sorry. That is just me zooming in on that graph. Okay? That's what that is. And when I take a graph with a corner point and I zoom in, I see a slope of one thing left of the corner and something different on the right, and they never agree and smooth out. All right? So that's what this means. We'll call one the left-hand derivative. Okay, here's our symbol for that. F subscript minus prime. And a right-hand derivative, F subscript plus prime. That's the slope just to the left of the corner point. It won't be the same as the slope just to the right. All right. So that's the more technical aspect of it. Remember, when you're looking at this, that should be h goes to 0 from the right there. All right. Now, for me to give you an example of a graph or a curve that has a corner point, it would be this one in this problem. Okay. Now, here's what it's asking. You see that part. There are those definitions of the right and left-hand derivatives. Okay. Which I suppose, if you read this question, would give you the impression that we have to calculate them that way, but we don't. All right. So my curve is f of x is absolute value of 2x minus 8. And I noticed that they provided me a graph here, but I would like to redraw the graph. Okay. So here's my recreation of the graph, and I've labeled some points there in red. Now, in part A, it says sketch it. Okay, so you can sketch it with the grapher over there, and I've drawn it here. Part B says compute the right and left-hand derivatives. Here's how we would do that. You don't have to use this. This one's simpler. So looking at this curve, do you see that this curve, and I say curve in quotes, this is not curved, but do you see this function, this graph, is two lines that meet at what appears to be a corner point. If I look at the line right of the corner, it is a line, and I can identify 2 points on it. And I can tell you the slope there, right of the corner, is 2. And you see this point, or this part right here, left of the corner, it's a line. And I can tell you the slope of this line, left of the corner, with those 2 points, and it's -2. So those are the derivatives, basically. The derivative over here, meaning what does the derivative tell you? One thing it tells you is the slope of the curve. Okay, so at every single point on the curve, right of the corner, the slope is 2. So the derivative is 2 everywhere over there. So I could say the right-hand derivative is 2. And then left of the corner, it's a line. The slope at every single point over there is -2. So the left-hand derivative is -2. But we said a corner point is such that the left and right-hand derivatives at the corner don't exist. So yes, like right at 4, to the left, the slope's -2, to the right is +2. So the left-hand and right-hand derivatives are -2 and +2, and they're not the same. And because they're not the same, that's the definition of a corner point. All right, so that's the basis on which I say there's a corner point at 4. So look at the answer. See how I put there the right-hand derivative at a, which is the corner point. In my case, that's at 4, is 2. In the left hand is it -2. All right. Now, one more thing I'll say is, yes, 4 would be a critical point because the derivative is undefined there. Okay. There is no way for me to tell you the slope of the curve at 4. On the right, it's 2. On the left, it's 2. But at 4, there is no derivative. It's undefined there, right? If I zoom in more and more at 4, I don't see this picture morph into a line that I can measure the slope of, okay? So it's undefined at 4. There's no f prime of 4. That's a critical point. It happens to be in this third possibility. There's a critical point there because it's a corner point, okay? And one thing that I haven't emphasized so much in this video is, what is the derivative? Well, if you want to know the derivative, I wouldn't really use any rules to find the derivative of this. I would just give it to you this way. F prime x is -2 if the x is less than 4, and 2 if it's more than 4. What's the derivative at 4? Does this definition include 4? No, because the derivative is undefined. All right. Okay. So there's my answer. I guess to answer C, we would say it's continuous there. All right, there's no discontinuity at 4, but it's not differentiable. Okay, the derivative does not exist there by nature of having a corner point. All right, so now what I hope this video has done is showed you how to solve this problem and understand what they're asking. But in addition to that, as we will see lots of talk about critical numbers and critical points, and having that reference that the derivative be undefined some of the time, that now you know what that could take shape as, how that looks. That the curve is either just not continuous to start with, that it's vertical somehow, or that there's what we call a corner.